In this section, I introduced the idea of an exponential function, and exponential functions are functions that have exponents, but they're not like polynomial functions. Remember, like x squared and x cubed, they have exponents, but they're not exponentials because exponential functions have the x in the top. Okay, so the power is where the x is, and the base is like a constant number. Okay, so 3 to the x, 5 to the x, even things like 1/2 to the x is an exponential function. Now, the graph of an exponential function can either look like an exponential growth, hello, or an exponential decay. Yeah, they're from yesterday, or 2 days ago, right? Mhm.
Oh.
Yeah. All right, and we did some practice doing the graph of exponential functions, which we actually, well, that's going to be on your quiz. So we did some stuff with that. But there's actually a little bit more with exponential functions. The idea of exponentials expands wider than just drawing the graph. There's actually a lot of applications of exponential functions as well that we might touch, but I don't think we have enough time for that. Okay, and the reason that they're so important is because exponentials do something different than polynomials. Okay, for example, the graph of f of x equals x squared. Okay, that's not an exponential, it's a polynomial function. If I plugged in numbers into this graph, okay, found x values and y values, I could plug in like 1 and get 1. I could plug in 2 and get 4, 3 and get 9, 4 and get 16, and so on. Oh, you're okay. So I can plug in numbers and it does grow pretty fast. Even if I plug in 5, I get 25, which is a lot bigger than what I started out with. Okay. Now, exponential functions, on the other hand, they grow a little bit faster. And what I mean by that is if I switched around the exponent and the base. So if f of x actually equaled 2 to the x, okay, I could also plug in x and y values. Okay, if I plugged in 1, I would get 2. If I plugged in 2, I would get 4, which is still the same as the last chart here. But once I plug in 3, I'm going to get an 8. Okay, a little bit slower. But once I plug in 4, 2 to the 4th power is 16. Okay, I can plug in 5 and get 32. Okay, so in the very beginning, it looks like these numbers are matching, right? Like 4 and 4. Then around 3, it looks like 2 to the x is a little bit lower than x squared. But once we hit 16 and I plug in higher numbers, the exponential function is going to produce greater values than x squared. So it's going to grow a lot faster. That's what I mean by that. Okay. The reason why exponential functions are so widely used is because a lot of things grow really fast. They grow exponentially. For example, populations grow really fast. The more people you have, the more people you will have in the future, right? And even money. If you ever do like a banking example, you might see this equation here, A equals P times 1 plus R to the X. Okay, we won't do much with that, but this equation is used in a lot of financial mathematics. Okay, so this has a lot of financial applications. Okay, now I'm not going to go into how this happens. Okay, I'm just going to kind of tell you the result of this. If you use this financial application equation, and you do something weird with it that is more widely used in calculus, okay? This number comes out of it, okay? This number is derived from the equation I just wrote down, okay? I'm saying number, but I wrote down a letter, which is kind of confusing, okay? This number is kind of like pi, okay? Any questions so far? I do want to go to the next page real quick. So let's go here. So I wrote down this number E, okay? And before we even talk about e, I want to talk about pi, okay? Pi is a number. Does anyone know what it is? 3.14, right? Okay. Now, whenever we see pi, we always know that it's just 3.14, okay? The same thing actually goes with this number e, okay? Anyone know what e stands for? Mm-hmm. Oh, that's so close. It's 2.718. Okay. So just like pi, whenever you see this number e or this letter e, all you have to know is it's just a substitution for 2.718. Kind of like how physicists use like c for the speed of sound or speed of light, right? I know physics, right? But whenever you see that number, don't be scared. It's just a substitution for a specific number that is used a lot in exponential applications. Okay, now this number has a very specific word for it. We call it the natural exponential, okay? And the natural exponential function, because we're talking about functions here, is literally just this 2.718 value e raised to the x power, okay? So it's literally just a number raised to the x power. Okay, well, let's do some practice for our quiz. Let's actually draw this function, okay? So I told you whenever we do exponential drawing in this class, we always plug in some points, right? So we plug in x and y, okay? Easiest point is x equals 0. When x equals 0, what is y for any exponential function? Oh, it's 1, right? So this is one that you can either memorize or just, oh my gosh. You can either memorize or just learn that this is always true for exponentials, or you can just plug in 0. Okay. What about 1? What would I get? 2.718 or e, right? So e or 2.718. Okay. And I guess we can even, I didn't do this in my notes, but we could plug in -1, right? So that would give me what value? Well, give me e to the -1. And what's another way of writing that? 1 over e, right? Well, 1 over 2.718, because substituting 2.718 for e. And I guess I'm going to have to do this division on my phone because I didn't do this before class. I'm getting 0.368. Okay. So we have 3 points that we want to plot. I definitely have 0 and 1. Okay. I'm definitely looking for this point on my graph when you graph it. Okay, so make sure you have that point down. We have 1 and 2.718. And then we have -1 and 0.368. Okay. Now the exponential function always has this shape, okay? And there is a natural kind of asymptote going on here at the x-axis because our graph gets really, really close to the x-axis, but it never touches it. Okay. So the natural exponential function looks just like an exponential function, okay? It's just a weird number on the bottom. Okay. Any questions so far? All right, let's flip our page over. And we're going to start talking about something that I think is really scary to people when they see the symbol, because I feel like you guys haven't done this for a really long time, but I promise you it's not that bad. Okay. So how would I find 2 to the 5th power? Good, right? That was kind of what we did in the beginning of the semester. To find 2 to the 5th power, I would take 2 and multiply it 1, 2, 3, 4, 5, and that actually gives me 32. Okay. Now, when we deal with exponentials, we're usually used to writing it like this. We usually do this. We say 2 to the 5th power equals 32. Okay. And I like to label what each of these letters or numbers are just so we can switch them around a little bit later. Okay. So bear with me here. 2 is what we call the base, right? We can also call it like the growth rate, but I don't really use that. Okay. 5 is the exponent, or how many times we multiply something together, right? So this is the exponent or the power. Okay. Now 32 doesn't really have a name, but I usually call it the final result. Okay. The final result. Okay. So we are going to talk about a different way we can write this. And it looks a little weird, but I promise it's not that bad. Okay. Let's go into this chart. The first cell says 2 to the 5th, which we know is 32 from up top. Okay. I'm going to write it in this form that's called a different name. Okay. But it says the same thing. Okay. We're actually going to go into logarithmic form. Okay. Does anyone actually know how to write this in logarithmic form? It's been a while, right? All right, let's go into here. Okay. In our second column, I'm going to rewrite this as such. Okay, I'm going to write log for logarithm. Okay. I'm going to put 2 on the very bottom. Okay, so the base kind of goes on the bottom here. Okay. I'm putting the final result next to my log, but up top. Okay. And I'm going to say that this equals 5. Okay. So essentially what I'm doing is I rearrange all the different letters. So 2 is still my base, but it's in a different spot. My final result doesn't come last, it actually comes second. Okay. So this is the final result. And then 5 is the power. Okay. So instead of saying 2 raised to the 5th power equals 32, it's essentially saying I need to take, 5 is the power I need to take 2 to get the final result of 32. An easier way of saying that is log base 2 of 32 equals 5. Okay, so that's how we pronounce this. Okay. Let's do a few more examples just to figure out all the different things that can happen with this logarithmic form, and then we'll kind of put it into context here. Okay, what's 2 to the 0 power? 1, good. Okay, any ideas on how to write this in logarithmic form? Will? Perfect. Log base 2 of 1 equals 0. The power goes on the end. The final result is kind of in the middle, and 2 is the base of the log. Okay. Okay, of course we would say log base 2 of 1 equals 0. Let's do one more just to show you what can happen with logs when we have fractions going on. What's 2 to the negative 1st power? 1/2, good. Okay, now even though we haven't dealt with fractions with logs yet, we can still do this, okay? This would be, or any ideas on how I could write this? Log base 2 of 1/2 equals -1, good. Okay, so a log can have a negative value, and yeah.
How is it?
Because the power always goes on the outside, right? So this power always matches the exponent. Same thing as how 0 matched the 0 here, and how 5 matched the 5 there. Does that make sense?
So the power is always the answer.
Yep. So we're just rearranging how we write our exponents. It's a different way of writing exponentials.
Okay.
All right. So we basically have this idea of a log function, right? Log is doing something to a number, and we're producing the exponent. Okay. All right. Let's do an example as on how I would ask you a question about logs, and how we can basically solve logarithms, which is how we say this, okay? So in this example, example 6, I'm asking you to find log base 3 of 81. Now, I didn't give you the exponential form yet. I just gave you log base 3 of 81, and I want you to figure out what that equals, okay? Before we go and do this question, I kind of want to rewrite this so we have a better understanding of what this is telling us to do, okay? So log base 3 of 81. There's two ways I would say you can go about this. You can either think of this conceptually, or you can kind of think of the symbols in different places, okay? So let me do the symbols first, okay? Now, going back to how I labeled everything in my chart here, I know that 3 is the base, okay? And I know that 81 is the final result. Okay, now this question is asking us what this log equals. So we're asking essentially, what does this log equal to? Okay, well, we know that the question mark or the thing at the end is always the power of the exponent. Okay, so if I wanted to rewrite this using my exponential form, how can I go backwards? Three to the, well, question mark this time, right? 3 to the question mark equals 81, right? Where the base of the exponent is where we normally put the base. The final result is here. And the question mark is still the power. Okay, so I'm just rewriting this in terms of how I would solve this. So essentially what we're doing is we're doing exponentials, but backwards. We're doing an inverse of an exponential function, okay? Now, what power of 3 equals 81? Is it 4? I'm not very good. I think it is 4, right? Okay, so question mark equals 4. Okay, so 4 is my answer to the log. Okay. All right. Now it says in the next part of the question, how would I write this answer in exponential form? I know that the answer is 4, so I can literally substitute 4 into my question mark. So this could be 3 to the 4th power equals 81, and that's my exponential form. Okay. Any questions on logarithms? Okay, I promise we'll do a lot more examples with this. And I know it's a little confusing because I feel like we haven't done logarithms for a while. I feel like it's not something that you see every day, unlike like polynomials and things like that. Let's move on to a slightly harder question because it involves fractions. All right. Example number 7. We want to find log base 4 of 1/16. Okay. So rewriting my question, this is telling me to do log base 4 of 1/16, and it's asking me what that number is. Okay. Well, let me just label everything so we're on the same page here. 4 is what we call the base. 1/16 is our final answer. And the thing at the end is always the power, right? Okay. How can I rewrite this in exponential form? Good. 4 to the question mark equals 1/16. Okay, so essentially this is asking us, what power of 4 do I raise it to get 1/16? Well, that's kind of a little tricky because usually when we take powers of numbers, we get not fractions, we get whole numbers, right? Any ideas on what I might raise 4 to get 1/16? -2, right? So you thought about negative numbers as well, right? So when you think about what power you raise things to get something, also think about negative numbers. If there's a fraction in my logarithm, it means that the answer has to be negative, okay? So 4 to the -2 is 1/4 squared, which is 1/16, okay? So negative numbers here are fair game. So that means the answer to my log is -2. Any questions? All right. Example number 8 has a couple different examples here. What I want you to do is give these 4 questions a shot. Yeah, I think I'll let you do these and we'll come and talk about it in a minute. It makes you think a little bit harder than what we've been doing before. Okay, example number 8, the first one asks us to find what log base 3 of 9 equaled. Who wrote this one up? Allison, do you want to take us through this one?
Yeah, so just put it in the exponential form. And then I just know that 3 squared is 9. So.
Yeah, right. Now, honestly, like once you get here, you can just start plugging in numbers in your calculator, like 3 to the first power, and you're gonna get 3. And you're like, okay, that's not 9. Then you'll plug in 2, and then you'll be like, oh, 3 squared equals 9. So it's kind of like a guess and check once you get here. But nice job on that, Allison. Any questions on log 3 and 9? All right, then I think Stephen wrote up log base 5 of 625. Stephen, do you kind of want to take us through this one?
Oh,
Yeah.
yeah. So I just did what we did for all the previous problems.
Mhm.
Put the question mark on the base, and then I figured out that the question mark was 4, so 5 to the 4th power.
Perfect. Now, one thing I want to say about Stephen's answer is the answer is 4, right? So I like how you wrote it out in exponential form. That's totally fine. But like if you were to type this into WebAssign, you would write 4 as your answer. Mhm. But very nice job there. Any questions so far? All right. Finally, something very similar to example number 7, we have log base 6 of 1 over 6. Who wrote that? Was it Marissa? Do you want to take us through this one?
Yeah, so I started by rewriting it just because that's how I think. And then I rewrote it into exponential form. And then I realized that it's the same thing, pretty much as the one that we did above. So I realized it was negative.
Perfect job. Any questions on the negative one here? All right. The last one was a little bit tricky. I didn't really tell you how to do this one yet, but I did want to kind of make you think a little bit. So this one asked us to find log base 4 of 2. Okay. Now, same process of writing out this answer. We want to find what this equals. So another way of writing this is, well, 4 to the what power equals 2. Okay. Well, usually with exponentials, we get a little bit bigger, right? And even negative numbers wouldn't work because that would give us a fraction. Okay. So I could I could plug in some numbers, like, so on the side, I could do some work like 4 to the first power, and that's 4. 4 squared gives me 16. 4 cubed is 32, and that's not going to help. I could plug in negative numbers, like 4 to the negative 1, that gives me 1/4, but those numbers don't work either. Any ideas on what else I could plug in?
You can put in a fraction.
I could plug in a fraction, right? I didn't talk about fractional exponents yet. Let's do, I don't know, 4 to the 1/2. What essentially is a half power? Square root, right? Remember, a half power is also the square root of 4. And what's that? 2, right? So we did find a number, 1/2, that we can raise 4 to get 2. And it's actually not a negative, it's not a whole number, it's actually a fraction. So the answer to this one is a half. Okay. I know it's a little I know there's a lot of numbers going on. There's a lot of fractions and negative numbers going on. But fractions are also fair game for logarithms as well. Any questions on example 8? All right. Checking out the time here. Looking at my quiz review, I think it's a little bit longer than I kind of meant to. So I think I'm going to start this now, just so we have enough time to go over this quiz.